Welcome back to Advent of Code 2022. I'm John Eisen. I'm going to solve day 12 for us here, and should be pretty fun. Let's get started. Hill climbing algorithm. You try contacting the Alps using your handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above broken into a grid, the elevation of each square of the grid given by a single lowercase letter, where A is the lowest elevation, B is the next lowest, and so on, to the highest elevation, Z. Okay, so elevation is given in letters. Also included in the height map are marks for your current position and the location that should get you the best signal, E. Your current position has elevation lowercase a, and the location you need for the best signal has elevation Z, okay? You'd like to reach E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, or right. To avoid needing to get out your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your elevation is M, then you could step onto elevation N, but not elevation O, because you can't go two up. Can you go down as well? Yeah, it seems like you can go down. So we have to, that's probably a trick that the input will have, is that you can possibly go down or stay the same, and you have to sort of handle that. Okay, so S, A, B, C, 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 D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, 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 Y, Z, E. Cool, so that's how the route goes. So this is, almost all these Advent of codes have a shortest path problem. This is a shortest path problem. So our job is to implement a shortest path algorithm. Yeah, we'll be doing that today. So hope you guys will enjoy me trying to remember how to write Dijkstra's algorithm. Let's copy this input while we're here. And we already calculated the example. So, and then this takes 31 steps. So that's this. Okay, let's get the input. All right, so yeah, we understand what to do. Just have to implement a shortest path algorithm. Pretty simple, actually. There's not even a weight system between each step. Each step is the same weight, meaning it's the same cost. So should be pretty good. All right, so we got a grid. Is a list star, and our input is a grid. Okay, and each star is going to be a, and then we're going to be a height, right? And we're going to have start is a position. Int, so create a position, and we have an end position. All right, so let's read the input. So grid equals raw.split lines, and then it's line.split on the empty string for line in raw.split lines. So that'll give us every character. And then we're gonna do start equals, we're gonna find I, J, for I in range grid, len grid, for J in range len of grid 0, if grid I, J is equal to S. We're gonna do the same thing, and then we're gonna get the first value of that list. And we're gonna do the same thing for end, whoops, key bindings. Cool. And then we just put this in the input. So start equals start, end equals end, grid equals grid, kill all that. And we've got our parsed input. Nice. So let's do our shortest path algorithm. F shortest path. And we're just gonna take the input here. Okay, so what do you need to write a shortest path algorithm? Good question. First of all, you need a current position. Input.start. Secondly, you need a possible places to go. So from a current position, where can I go? So destinations. And we're gonna find the grid there. So, okay. So then the possible destinations are up, down, left, and right. We're gonna do I, J, or we'll call it X, Y equals cur. So we split it out, and then we have X plus 1, Y, X minus 1, Y, X, Y plus 1, X, Y minus 1. So those are possible destinations we can go. Oh, we forgot something. We need a visited list. We need a list, or a set actually, of visited nodes, visited positions. Because if you're doing a shortest path, you never want to retrace your steps. That would, by definition, be not the shortest path, because you are doubling up on one node or more than one. So visited equals set, and we'll keep it empty for now. And so first of all, there are 3 checks we want to do for these destinations. Are they outside of the grid? What is the current height of the current height, and the difference between the current height and the destination height? And, or is it in the visited set? So for dest in so first we check if it's in the visited set. Why invalid? Oh, there's 2 4s here. Okay, all right. Then now we're gonna check if it's outside the grid. So we're gonna make a little helper function here. Def in grid pos position bool. So xy equals position if x is less than 0, or y is less than 0, or x is greater than len of grid, or y is greater than or equal to len of grid 0, and this is greater than or equal to, and we'll just return that. So, and in grid. All right, so now we're checking for if it's not in the visited set and it is in the grid. All right, so that's good. And then we have, we're gonna make a height helper function, grid pos position, and we're gonna return a stir, right? Or we'll map it to ints actually, so we can do subtraction math on this. So we do xy equals pos, height h equals grid x grid y, and then we do if h is s, return ord a, elif h is e, return ord z, else return ord h. So ord is, we used this in a previous day. Ord is the function that maps a character to its integer representation in ASCII. And so A through Z are ordered right next to each other. So if you subtract them, you get, A minus B is ord A minus ord B is going to be -1. And so that's really going to help us going at most one height up. So, all right, so then we want height. So we'll do cur height equals height grid cur. So we're going to get the cur height, and we want the height of the destination square minus the cur height, the current height, to be at most 1. So less than or equal to 1. So this is going to be D for, we're just going to do return. And we're going to have our 3 conditions here. And in grid. And then we're going to do this one. And that. And now we have our 3 conditions. D, a destination is not in the visited set. It is in the grid. And its height is at most 1 more than our current height, and that would lead us to our possible destination list from any given current position. Nice. So actually we can just do grid here. And we can move this outside of our shortest path. All right, did that work? Mostly. Okay, all right. Sorry for the flashy things. I was selecting all and tabbing. All right, so destinations is written, and this returns a list of positions. Nice. Okay, so now we have our shortest path. Now we need to write our shortest path algorithm, which now is pretty simple. So while cur does not equal input.end, right? Sorry, thinking. We can either do a breadth first search or a depth first search. Oh, right. All right, sorry. I'm remembering how to write these algorithms. Thank you for being willing to listen to me. All right. So, instead of keeping a visited set, we have to keep a map of each node or position to a distance. So what we actually want to keep is a distance map, and this starts with the input.start and has the distance 0. And we have our current we're going to remove this. All right. We're going to remove that visited check from the destinations. So we'll do that outside. All right. And then we have a current, we'll call it heads. So this would be a breadth first search. So we're going to keep the head of our paths, right? Oh, and then we have we start with unvisited. Oh, we start with neighbors. We have a neighbor list, right? Of course, we have a neighbor list. Okay, all right. Neighbors equals destinations grid input.start. So right? All right, I'm thinking out loud. Sorry, I'm trying to think through this algorithm. I could look it up, right? But I'm trying to remember all the many times I've written this. So essentially the algorithm I'm thinking of is we keep this list of the distances to any given node. So we have a list of neighbors, and this is going to be a set of neighbors. And this is going to be, we're going to start with the input.start. And we have a list of distances, and this is a dict of position in 2 ints. And every iteration, we are going to pull a value from the neighbors list and calculate its distance. And we're going to put that in the distance list. And we're going to take all of that current node's neighbors and put those in the neighbors list with a distance in them. So the neighbors list is actually a list of tuple of int and position. And that way we order the list, so we always pull the smallest. So, and our algorithm ends when the end position ends up in the distance list. So when, well, input.end not in dist. And then we want to return dist of input.end, because this returns the number of steps to get there. All right, so our current node is going to be, so neighbors.sort. We're going to sort the neighbors list based on the distance to them, and then we're going to pull the first off. So current and neighbors equals neighbors 0, neighbors 1. So we assign neighbors to be the rest of the list, and we pull the current one. All right. So then, and we have distance and cur position equals cur. So we're split. Remember, this is a tuple of distance to position, so we split that up. So now we have the distance, right? And we add it to the distance list. So distance is cur pos equals dist, right? And then we do for destination in destinations grid cur pos, so cur position. We want to check if that destination already is visited. So if dest in distances continue, so break out of this for loop or go to the next iteration of the for loop, else then we want to add it to our neighbors list. Neighbors plus equals the current distance plus 1, because that would be going to this spot, and current, and then the destination position. Okay, so I hope I'm doing this right. So if I get flummoxed later and can't implement this, I'm just going to look it up. But I'm really enjoying trying to remember how to write this algorithm. So yeah, this should be good. This should be a nice breadth first search. Why is it breadth first? Well, it's breadth first because we are always taking the shortest distance neighbor and going there before going to the longest distance neighbor. it would be depth first if we took the last position in neighbors. And maybe that'll run faster, but maybe not. It really depends on the algorithms, or it depends on the actual grid itself and how it's organized. The input could make a grid that breadth first goes first, and could make a grid that depth first would return first. But they're both of the same order of magnitude when amortized over all sorts of grids. So it's not too big a deal. How long is this going to take? Well, it will take at most the size of the grid, which is, we'll just call it n squared, right? And because every single iteration here, we add one of the neighbor list into the distances. And so eventually the end position will end up in the distances dictionary, and we will return it. So it will run at most n squared times. And then each time we will be sorting the neighbors list, which I suppose could get upwards of the size of n. So that's n log n, right? So then you could have n cubed log n. So this would be very, bad. So maybe it's best to, when we add to the neighbors list, we put it in order. So let's make a function here to make it a little bit faster, so that we always insert in order, which is O of n, not O of n squared. So if we always assume neighbors is ordered, so def insert ordered, and we have a list of tuple of int and position. So we have list, and we'll call this ls, and what item is a tuple int position, and it's going to return this list. We could use generics here. I'm not entirely sure how to use generics in Python, but it doesn't matter. So for I in range len of ls, the list, if lsi is greater than item, then it's the first one that's greater than the item, then we want to insert before I. So we return ls 0 up to I minus 1 plus the item plus the ls I colon. So, and then if that never hits, then we want to return ls plus item, put it on the end, and this will always insert ordered. So and it'll do it immutably, which is nice. All right, so now we've lowered from n cubed log n to n cubed big O notation, and we should be ready to try it out. Return shortest path input. All right, let's try it out on the, I installed Conda, so hopefully we can get some better usability here. Day 12, Python, day 12, example, empty separator. Yeah, I know, I suppose, yeah, all right. You don't have to split on an empty separator. You can just pass a line, because strings act like, they act like lists. Height, missing one argument, grid and position. All right. List index out of range, grid xy on height. So that means in grid passed. So, oh, this is returning the opposite condition. Oops, not this. All right, we got 31 for the example. Let's see how that's the correct answer. Let's see how long it takes to run on the input. List index out of range. It ran out of neighbors. Very interesting. That means we have a bug in our implementation. But let's do this. If len neighbors is 0, import ipdb.setTrace. Let's debug at this position. Pip install ipdb python. All right, we're just gonna quickly install some things because I didn't do this before and I just set up a new conda environment. So, all right, we're gonna rerun here and we should hit this condition because neighbors is empty. So we have neighbors, empty list. All right, distances. Okay, input.end is 2058. Distances.getInput.end, not in there. Len of distances, 304. Len of grid times len grid 0. How many positions are there? It's 3,000 positions. All right, so we got to we're clearly not navigating correctly, or else we would have basically, I think the bug is that something in one of these destination lists is incorrect. Like we are filtering our destinations too much. So I'm going to take a look at this. Let's take a look at this input. So where do we start? Where's S? Here's E. I don't see S, but it's somewhere in here. You know what? Let's add this stupid condition. This probably won't work because this is probably the trick. I don't know if we should do that. That's probably the trick, right? Like, is that you have to go down to go up. Where is S? Where's capital S? Highlight all. Oh, here it is. All right, so yeah, so A, B, and then you can find C. You can traverse all the C's until you get to D is up here, and then D can go to E. Where's E? D can just go to E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T. Where's T? don't see T. Is that why it's running out? Wait, is it S-U-T? How's it? How's the alphabet go? Oh, here, these S's. Ah, so you have to go R, S, back down to Q. Wait. So we start with, there's R. So we're P, and then we're Q. There's Q, and then you got to go to R. So you're in that Q, you got to go to R. Then you go to S, and then you have to go down to Q. That's the trick. So you have to allow it to go down, and then from Q, you go back to R, but this time you're on this lower one, and then you go up to S, and then you go to T. So that's how the route will go. U, V, W, X, Y, and Z. Okay. So yeah, you have to allow it to go down. It's in the route. So why aren't we adding? So let's do print pos height grid pos dest So we're just going to add some print statements here. And just take a look, right? All right, so right before we run out of neighbors, we're on 3634, which is, I don't know, probably somewhere in the middle here. And possible destinations are 35, 34, 36, 35, 36, 33, all with the same height as our current. 97 is A. You know what? I think we should do... We should probably be doing a depth first search where we sort on the height of the position. So we go to all the highest heights that we can, instead of sorting on like the lowest distances. So I'm gonna look up depth first search and make sure I'm doing this correctly. Label V is discovered for all directed edges from V to W that are in the adjacent edges. If it's not labeled as discovered, then recursively call depth first search. Right. This would be depth first. All right, so this doesn't allow us to like sort by our thing. So let's so instead of tuple int position, we want to do int position, where that is the heights, right? Neighbors at heights, because we want to pull out maybe we do a dictionary of height to this list. All right, so I'm just thinking. All right, so highest height is neighbors.keys, and it's the max of that. So then, oh, we don't want to be sorting everything because we're inserting ordered. Okay. Actually, it's K for KV in neighbors.items where len of V is greater than 0. And that's if len of V is greater than 0. So if there are neighbors in the list, get the highest key. For that, so the highest height, then we are going to pull out height, and we're gonna pull off the first item from that neighbors list, but in this case we are also indexing by the highest height. We are spelling highest height very wrong. All right. Right, this is just a little helper for me to make sure that we're a little helper assertion, make sure we're doing this correctly. So if we're pulling out our neighbors list from a given height, it should equal the height of that position. The distances of the current position will be set, right, as visited. And for destination, we want to add it to the neighbors list, but at the height of the destination. Right, okay. Cool. So now we've changed the algorithm to go through the higher heights first. int object, not iterable. Neighbors is a dictionary. Items gives you KV. Yeah, 97,000. All right, so that's fine. 97 is the ord of lowercase a. Neighbors.items K for KVN lenv max oh right, okay, just syntax here, don't put this, don't splat the thing. Okay, all right. All right, let's get back to checking this. Highest height is not defined. We still cannot spell. All right, so the example still runs correctly with this change. We change the input. I'm going to remove all these print statements. Okay, well, it's not running out of space. Wait, are we looping over infinitely over the B's? Yeah, we're on 4-1 over and over again. Okay, that's a problem. All right. By the way, CHR is the opposite of ORD. So we're looping over B constantly. There's a problem in our algorithm. I'm just gonna make some things simpler so we can reason about them. Oh, well, that would be why. Still looping. I don't really know why. We should never be running on the same node twice. Because for each destination from the current position, if it's in the distances array dictionary, we don't do anything to it. And once you're a current position, you're in the distances array. I mean, I just added a case where that is not true, like, because we're not doing true breadth first search. Like, we could possibly hit a node and get to it faster. So I don't understand. All right. Destination 4-1 is not in the distances array dictionary. Oh, now it's really slow. That's weird. All right, well, here's a problem. Oh, we're out of 99s, I see. So we're on 99s. We do a bunch of C's, and then we run out of space to go. All right, 33.3. Where do we start? Oh, wow. Wait, okay. This is stupid. Oh, I see. Oh, of course. We're inserting nodes into the neighbors list very, like, more often, like a bunch of times. So we're going over the same node in the neighbors list over and over again. Okay, so in our insert order, we just want to make sure that the position, you know, I'm gonna make this easy on ourselves, and I'm gonna go back to our neighbors list being easier to use. So we're gonna make sure to make it a 2-level dictionary of position int. Okay. Nice. Okay. So we want to take the highest height and then the lowest position. So we're going to do, and then distance cur position equals the min v comma k for kv in ns dot items. Okay, this is very cool. So we are basically, I get the items list from this dictionary and I invert the key and the value so that this int comes first, and then we pull the minimum, and that gives us the distance and the current position. So we can eliminate this, and then we need to remove it. So neighbor's highest height equals neighbor's highest height cur position, and we need to delete that key from the neighbors list. Okay, we are sure of that, and then we're setting the current position to the distance. Yep, and then I'm gonna comment this out, and then insert order. Okay, so now we need to, now this is our insert statement, so the height and then the current, the destination, and it will equal neighbors.get dest height equals this. Equals neighbors.get dest height, otherwise the empty array empty dict dot get dest, or the grid, the distance plus 1. So we don't want to set, so we want to do the minimum of dist plus 1 and neighbors.get dist plus 1. And what this will do is it'll allow us to not insert the same node into the neighbors list over and over and over again, which is the bug that we currently had. So we are going to just insert it the one time and set the, and then when we insert it the second time, we're just gonna check which distance is less and insert that one. So, okay. Let's try this again. Oh, we got an answer. A key error, actually, sorry. Key error on... yes. So, if dest height not in neighbors dest height equals empty map, and then we can remove this. Okay. Example, still 31. Input 410. Hey, we got an answer. It's probably wrong. We probably have another bug, but I'm going to submit it anyway. Not the right answer. Good. Too high. All right. We have a working algorithm that we can improve. Yeah, let's just figure out what we're doing wrong. Did we have to cross back to Q? Yes, here's the SRQ. Because it should just go S to Q. So we need to keep running the algorithm until every... Let's remove this for a second. Let's remove it because now we have a working algorithm. Let's remove this, only take the highest height. And instead, let's revert back to the original algorithm we had where we want to take the lowest distance. So I'm just going to remove this outer dictionary here. We're going to remove highest height. Now it's 408. Why did this should work? It does. Why did that work? Well, part of the algorithm relies on always pulling the neighbor with the lowest distance from the start, because you can guarantee that the neighbor with the lowest distance, or the set of neighbors with all distances, will produce neighbors that also have the lowest distance from the start. And so you never get in the case where we got to before, where we got to the end with a slightly higher distance. So we got there with 410. We need to get there with 408. And the reason that we got there with 410 is because when we had to traverse from S to Q, we were biasing towards going through a higher node. And so it went through R. So we went SRQ. And I guess because we had to, I guess that just caused it to go through I'm not entirely sure where it exactly went, but we did see that when we changed it to only pull the lowest neighbor, and it didn't worry about this sorting. I was too worried about sorting, so that was the bug. But yeah, I'm glad we got that. We wrote a shortest path algorithm pretty much entirely from memory, which I am pretty proud of. As you walk up the hill, you suspect the elves will want to turn into a hiking trail. The beginning isn't very scenic though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start low as possible, elevation A. The goal is still to get to the square mark D. However, the trail should still be direct, taking the fewest steps to reach the goal. So you need to find the shortest path from any square at elevation A to the square mark D. Oh, so in this case, we can have many different starts. Huh. Well, all right, let's just start with a naive solution, right? Like, let's just run through every A and, override start, optional position equals none. All right, so we're just changing the start here. Yeah, let's just naively do it. I mean, maybe I don't think it'll take that long. There can't be that many A's. A's, all A's equals ij for I in range input.grid for j in range len input.grid 0. Forgot the len here. And if height grid input.grid ij equals ord A, return min shortest path input override start equals pos for pos in all A's. Yeah, I mean, I don't know, can't take too long. Examples 29, input min arg is an empty sequence. What? Oh, this ran out of neighbors. Oh, maybe there's some orphaned A's that we have to handle. So if len of neighbors equals 0, return 1,000,000. That will represent a failure. And then if there's an override start, then we never need to traverse to another A. So ever, right? Because that would, by definition, be a longer trail. So we're going to do another if statement. If override start is not none and height grid dest equals ord A, continue. And this is just a condition purely for the second part where we never need to go to another A, because that will by definition be like not a shortest path. So when we pass the override start, this little helper thing will prevent us from doing some extra work. And this will handle if we have an orphan position. So let's run it again. 399. Sounds right. That's correct. Awesome. So doing it naively took less than a second. So that was pretty good. We didn't have to optimize it too much. Yeah, I mean, the trick with this problem was writing a good shortest path algorithm that worked correctly. I had the right neighbors organization, but then the big bug was that we were inserting neighbors more than once. And I optimized before I needed to, which caused a bug where I was keeping neighbors as an ordered list when I never really had to, because the sizes here are just not that big. So, but we eventually got back to something that works and feels pretty clean. So I'm pretty happy about that. This is a little bit longer video, but these medium hard puzzles are going to be a little bit longer. But yeah, hope you guys enjoyed it, and I'll see you tomorrow.